Let's talk about inverse functions. Little graphic here shows that these two lines are actual inverse functions. So it's when you're going to switch the x and y. Excuse me. So that the two become inverses of each other. So you can see here if I come over to, if I head on over here to where x is 3, right, and I head on up and I look at this point here, okay, so that point right there is going to be 3, 4, right? Well, the inverse says the opposite is true, right? So where you switch x and y. So if I were to switch x and y, I'm going to get 4, 3, which happens to be right here, 4, 3. and it's going to be true for wherever you do this. So let's look at they're going to be inverses of each other, right? So let's look at this one. We've got -1, -2, and if I reverse those, it should be -2, -1. And if I go over to -2, -1, there I have it. There's my inverse of the function. Okay, so you're just kind of reversing them as we go, and we're going to use this idea to kind of graph and check answers of what inverse functions are. Okay, and really the main thing that's happening here, my understanding of why we use these is what it's really trying to do is to get to the point of what do you do when you're trying to figure out an exponent, right? You're trying to undo or reverse something to solve to figure out what an exponent is. And so this idea of inverse functions allows us to figure that out. So all right, let's take a look. We've got y equals x squared, and we have y equals radical x. Okay, so I'm going to just real quickly kind of go through here, and we'll graph. We'll go ahead and graph y equals x squared. We'll make it blue here. So 0, 0 is 1 point, and then I'm going to over 1, up 1. I'm going to go left 1, over 1. I'm going to go over 2, up 4, 2, 4. And then mirror it over here. I'm going to go over 3. I got a square 3, so I'm going to go up 3, 4, 5, 6, 7, 8, 9, and then 9. And then we'll go ahead and we'll draw our parabola here. We'll start here and we'll sort of make our way up. Okay, and we'll do it on the other side here, and we'll make our way up. Okay, well, if you remember from if you were in my class at least, we did an activity in Algebra 1 that talked about functions, what a function was, and we used Desmos in this thing called the function carnival, where we shot a man out of a cannon, and then he would parachute back down, and we chart his path over the course of his travels on a graph. And one of the things we really did is we kind of messed with the graph and like drew all over it, and we created things that weren't functions. And the idea was we wanted to see why this thing called the vertical line test works, right? So the idea of the vertical line test is that if I draw a line on here, it can only intersect it's only allowed to intersect any given point on this graph one time, right? So if I drag this across, it only hits one time, and that's how I can tell if it's a function. And really the reason why that works is because the definition of a function is for every one single input you have, you're only allowed to get one exact out. Okay, so you can't plug in one number and get two different results, and that appeared with our Cannon Man in the function carnival, that if you put, if you were to graph his, if we were to graph his time, right, his height compared to his time, right, like he was here and as he fell, it came down this way, right? And that would make sense because it all happened right there. But what we started to do is we started messing with it, right? We threw different lines in there. Well, what you look at is if I'm looking at any specific time, like let's say we look at this time right here and we go up from here, well, all of a sudden now he's appearing at 1, 2, 3, 4 different places. And all of a sudden you'd see like the pop in and out of existence of this Cannon Man, this man floating out of a parachute over at that one single time, which is impossible, which is why we say it's not a function. Okay, now because we are inverting this function, right, we're looking to see if it's a function. Well, it's a function now, right? It's a function this way. I can use my vertical line test, and I know that for every input that has exactly one output. Okay, but what's going to happen if I invert it? So what we do there is we use the horizontal line test, and the idea of the horizontal line test is to say, okay, well, if I were to draw this thing a horizontal line, does it interact twice, right? Because that's the general idea. What's happening here is, right, I'm going to reverse my x and y's, and we're going to see whether or not this thing is actually going to become a function. So you can see it hits 2 different times. And if you kind of turn your head 90 degrees, it kind of looks like the vertical line test, which you're going to see is sort of what happens here. Okay, so let's get rid of the green line. Okay, and I'm going to show you kind of how to solve, right? Well, how we do the inverse, right? And the idea of the inverse starts off relatively simple, right? What we're going to do is what I showed you previously, right? Where you take, right, x and y, and when you inverse it, when you do the inverse, you're going to make it so that it's y comma x, okay? You flip or reverse the two different functions, right? So x becomes y and y becomes x. And so what we're going to do, your input becomes your output and your output becomes your input. So what I'm going to do here is I'm going to go ahead and I'm going to write this, right? So I'm going to do y is equal to x squared, okay? And then I'm going to switch it. So y becomes x, and then I'm going to say is equal to y squared. But what the deal is here is that what I need to do is I need to solve for y, right? Y is the output, and we typically write these functions as the output is equal to whatever the input is, right? So now if I were to solve for y, I'd take the square root of both sides, and I'd take the so I'd get the square root of x, and that's going to be equal to y, okay? And what you can see here is if I were to graph this one is y is equal to the radical x. So if x is 0, then y is 0. Oops, I'm on the wrong thing here. I was on eraser. Okay, so 0 comma 0, and then what I'm going to do is if x is 1, then y is 1, right? And if x is, we'll go to 4, y is 2, and I'm hoping you can kind of start to see the symmetry that's happening over the yellow line there, the y equals x. Okay, then I'm going to go over to 9, and if I plug in 9, I'm going to come up to 3. Okay, and you're going to see, right? So if I go to, if I were to, chart this, this is, this point, and let's see, we'll come across here, right? We'll go this way, and this point here is 3 comma 9, right? Well, if I come over to this point here, well, this one is 9 comma 3, and you can see they've been sort of reverse, right? So, but the part that we don't see here is, right, is this part, right? This would be the part that was kind of that's not very accurate, but that's the idea. That's sort of this part here, right? Well, this part is not part of my domain because I have a radical, and I cannot plug in, right? X cannot be, X must be greater than or equal to 0, right? I'm not allowed to plug negative numbers into there and get a real number solution to plug in here. So that's the idea of what the horizontal line test does, is it gives you an idea of what type of things, right? If the result of what you're going to graph is indeed going to be a function, okay? And then if not, then it helps you figure out what your domain is, right? So we know that the domain for this function has to be that x is greater than or equal to 0, right? And that's going to have to be true here for the original one also. We have to restrict our domain so that if we're taking the inverse, we don't end up with non-real solutions, okay, or complex solutions. Whew. All right, let's move on. Let's actually find some inverses, okay? So y equals x plus 4. So what I'm looking for is the output of this one is the input plus 4. And then, so really all you're going to do to do the opposite there is to reverse it. So I'm going to say x is equal to y plus 4. Okay, so then if I solve for y, I'm going to get x minus 4 is equal to y, right? Or if I want to, I can say y is equal to x minus 4. Okay, so these are opposites of each other, right? So if you were to do that, it would be you'd end up with two different lines, right? And so if I wanted to, I could too. I'm just going to kind of put in a dotted line. This is about where y equals x is, okay? And so my original blue line here is going to just be, let's say this is 4, right? So that's b. It's just going to go up like this, right? And then it's going to come down, and it's going to follow. It's got a slope of 1. It's the same slope. And then if I were to do the secondary one there, I'm going to do an orange because I kind of messed up and made the middle one, right? It's going to be -4, right? Same idea, but you can see they're equidistant from, right? They're equidistant from that center line there because I mean that's just how you have to flip it, right? So get a general idea of what it looks like, right? It's going to be symmetrical over that central line of y equals x. All right, so those are inverses. Let's take a look at another one, okay? So let's find the inverse of a function, right? So now we've got function notation. So we've got our original function, okay? And I'm going to try we'll start it in blue. I'm going to try to keep the originals in blue. So we got the original function, right? F of x is equal to x squared plus 5. Well, we know that f of x is the output. That's the same as y, right? So that's the same as saying y is equal to x squared plus 5. Okay, well, now what I'm going to do is I'm going to invert this, okay? So I'm going to flip the x's and y's. So I'm going to say x is equal to y squared plus 5. And from here, I'm going to solve it. So first thing I'm going to do is I'm going to say x minus 5, okay, is equal to y squared. Then I'm going to take the square root of both sides. So I'll do y squared, and I'll take the square root of that side, and I'll take x minus 5, and I'll take the square root of that side. And I'm going to end up with y is equal to the square root of x minus 5, right? And there's some constrictions in here, right? Or restrictions in here as far as domain, right? The domain here, x can't be really anything less than or equal to 5, right? So x must be greater than or equal to 5, right? In order for this to be true, otherwise I'm going to end up with a negative number in there, okay? So, and now what we have is we have this, okay, is the inverse, right, of that. And the way we'd write that is we'd say f of, right, f negative 1 of x is equal to square root of x minus 5, okay? So that's the idea. Hopefully this is at least the beginning making sense, right? So now what we have is we have a function g of x is equal to the radical x plus 4, okay? And so now what we're going to do is let's immediately, first of all, let's go ahead and let's find the inverse of it, right? So we know that in the beginning it's we've got y, whoops, try to be consistent here. So we know that y is equal to radical x plus 4. So now I'm going to flip it. Right, so now what I'm going to do is I'm going to take those ideas and I'm going to flip them. So what I'm going to do is I'm going to say, all right, x is equal to radical x, whoops, no, not x, radical y plus 4. Okay, and now I want to solve for y. So the first thing I'm going to do is square both sides. So I get x squared is equal to y plus 4. Okay, squaring both sides eliminates that radical there. Then I'm going to say x squared, I'm going to subtract 4, and I get x squared minus 4 is equal to y, right? So now I know that the inverse function here is going to be x squared minus 4, okay? Well, what this next part is basically saying is if you plug in the inverse function into the original function, then what you should end up with is just x, right? Because this is saying the function of the inverse function should give you the original thing, right? Well, if x is the original thing I'm plugging in, and I take the inverse of it, and then I plug it back into the original one, I should just get back to where I am. Okay, it's kind of because you're moving forward, and then you're undoing what you did, moving backwards, or maybe you went backwards and you're undoing that, so you go back forward and you're back to where you started. So let's do this. So we know that g of negative 1 of x, okay, is this, okay, and we know that g of x is radical. We know that this is radical x plus 4, right? But x in this case is x squared minus 4, right? Because this right here is what goes in there. Okay? All right, so what I'm going to do here is, so x squared plus 4, that's my x, okay? And then plus 4, and I have to extend this out, okay? All right, so let's go ahead and let's simplify. So I've got x squared minus 4 plus 4. Well, I can open up these parentheses because there's just addition, and I just get x squared, right? Because minus 4 plus 4. Well, x squared, the square root of x squared is x. So there I'm at. Okay. So let's try the other one. So now what we're going to do is we're going to take g of x, right? Which is, we're going to do x squared. So I'm going to do x squared, right? Okay, that's where now we're looking at that top one, number 1, x squared up here. I don't know if you can see my cursor or not. What I'm going to do is g. So now I've got g of x, right? So I'm going to take g of x and plug it in. Okay, so what I'm going to do is I'm going to say radical x plus 4. Okay, that's this thing here. Okay, that's this thing here. Plugging it in there, squared, and then minus 4. Okay, so I'm going to square that, and I get out of the radical, and I get x plus 4, and then I subtract 4, and when I put those together, I end up back where I started, which was x. Okay, So really what this is helping us do is this is helping us figure out whether or not we inverted the function correctly, if it's the right inverse. Because if you plug this in and then if you do either one of these steps, right, if you do 2 or 3 and you don't end up with x, okay, then something is wrong. Then something is wrong because it needs to be x, right? Whatever I do to it, I'm going to undo. I should get back to where I started. The starting point in these cases is x. All right. So we'll go ahead and move on. I do want to show, before we get there, and this video is getting long and I apologize, but we're doing what we can. I did want to show you sort of an idea here of what this looks like, right? So this is f squared, right? So we kind of looked at that before, right? And so you've got a point here, right? So this point is 1, 1. I got another point here, which is, come on. I don't know. It's not liking it. No, okay. We're going to leave it. So that's 1, 1. And then this one is, the green one is the inverse of that, okay? So then what I want you to see is, okay, so here's x cubed, right? Here's x cubed, the orange one, okay? Well, the inverse of x cubed would be, if I flipped them, it'd be the cube root of x. So well, let's look at let's see what that looks like. And you can see it creates this symmetry, right? It creates this really kind of beautiful looking pattern where they become opposites. And you can see where they meet and intersect at certain points because the input and output are going to be equal at those places. So I know in Desmos they do some art on here. I would encourage you to look at some of it and how they get to it. And a lot of times they'll use inverse functions to create just some beautiful, beautiful artwork. So, all right, back to here. We're going to practice. So I would encourage you to pause the video and then come back and go ahead and see the answers. So I'm going to kind of try to quickly go through these. All right, first, I like to write it out as in the right color. I like to write it out as y equals 3/2 x to the 4th. And then I'm going to switch it, okay? I'm going to go ahead, since I'm already in blue, I'm going to write this one over here too. Y equals cube root of x minus 3 plus 15, okay? So now I'm going to go to red, and I'm going to just walk through this, okay? So I'm going to switch these, right? X equals 3/2 y to the 4th, okay? So I'm going to take the 4th root of this at some point, but at first I'm going to have to multiply by 2/3, right? So I'm going to get 2/3 x is equal to y to the 4th, and then we're going to go ahead and we'll take the 4th root of both sides. So I get 2/3 x is equal to y, right? So the 4th root. And you could write it also as 2x over 3 is equal to y. And I'm not going to bother with rationalizing that right now, so we're just going to leave it like that. Okay, so that's the general idea. Okay, let's head on over to this one. So I'm going to switch it again. X is equal to cube root of y minus 3 plus 15. Okay, so before I can cube this, I'm going to need to move this over to the other side. So it'll be x minus 15, okay, is equal to the cube root of y minus 3. I'm going to cube both sides, right, so that I can get to y by itself. So I'm going to get y minus 3, and then I'm going to do x minus 15, and this is going to be cubed. Now, I'm not gonna expand that out. We don't really need to, because it's not really the idea here. So what I'm going to do is just solving for y, because a lot of times all you're doing is try to generate a graph or input-output table, and this is actually easier to graph this way than it would be to expand it all the way out. Okay, so I'm going to end up with y is equal to x minus 15 cubed plus 3. Okay, and we can go ahead and pick a number if we wanted to. In fact, let's try 3, because or if I plug in 3, I get 3 minus 3. Let's put in 4, right? So if I put in 4 minus 3 is 1. Cube root of 1 is 1. 1 plus 5, so I get 16. So this is 1 comma 16. Okay, so then let's take a look here. And what I should get is, if I plug in 16, I should get y is equal to 1, right? So it's 16 minus 15 is 1. 1 cubed plus 3 is, wait, let's see what happened right there. 16 minus 5, 3, 1, 4. what did I plugged in 4 here. Whoops, sorry. So, and it does work. So 16 comma 4, right? And what we could do too is we could take this whole piece right here, right? And we could plug it in for x. And if I solved it all the way through, I'll end up with x, which is what's supposed to happen. Okay? Okay, last part that was requested in this video. It's a real quick something. It was really the idea somebody said, asked about the difference between linear and linear and discrete. Well, linear just means line. Discrete means non-continuous, right? So a lot of times you'll see a graph. If you ever see a graph that looks like, whoops, let's see. If you look at a graph that looks like, come on, you know, it comes over, okay, like this is a continuous graph, right? There's no holes in the graph. If I go this way and it's, you know, dot, 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 this would be discrete because it doesn't, there's no line, it's not continuous. There's nothing in between, right? Like in this area and this space, there's nothing, and then there's a point here. So it's not a continuous function, right? So a discrete function is something, you know, oftentimes when you can just use whole numbers, right? So here's some, you know, you pause the video and just kind of look at the examples of what it is, right? But the idea of discrete and continuous is just that you can't look at the in-between. A lot of times it just means no fractions. This is the real life version of it. Whew. Okay, that was long and a lot, but hopefully it helps you, and yeah, good luck.